Hello and welcome to chapter 13. So this chapter covers the death of stars. We know by now that it's a misconception to say that stars are fixed and that they don't evolve and that they don't change. We know that that's a misconception, and we know now that stars are born, they evolve, and eventually they die. A lot of that death, or a lot of the reason behind that, is gravity, and we'll see that in a little bit. Let's first go on to our learning goals here. It's a good outline of our chapter. And then, so just a little recap again the formation of stars. Stars are born, they live a finite lifetime, and then they die. They're formed during the collapse of the cores of giant molecular clouds. So these clouds are molecular clouds. These are the interstellar medium that we looked at in chapter 10. So that interstellar medium, within that medium are these giant molecular clouds. So molecular are molecules, often hydrogen and helium. So these clouds contract, and as they're contracting, they're heating up. So think of when you're, a way to understand how contraction makes you heat up. Think about when you're cold. Your natural inclination is to rub your arms around yourself and to like snuggle up and pull a blanket around you and snuggle up. So you're contracting, you're pulling things inward and trying to keep that heat inside. So when a cloud contracts, it's going to heat up, and it heats up to the point where it gets so hot that it ignites a thermonuclear reaction or a thermonuclear process. And we'll get into that in a little bit, or we already saw that. Factors that resist the collapse is thermal energy creates a lot of pressure, and then magnetic fields surround the stars. The stars rotate just like the planets do, so they have angular momentum, and then there's a lot of turbulence going along. It's not a mellow atmosphere. There's a whole lot happening in there, and all of that turbulence feeds off of itself. So when they contract, there's some kind of an external trigger that has to make that cloud contract. And so some kind of an external trigger initiates the collapse of that cloud. It could be a wind. We saw in the last chapter that little Viking helmet looking cloud. That was a big solar wind blew by and created that bubble, and that was surrounding that star. And here in this case, we see the clouds actually beginning to deform and collapse in on itself. It's getting more dense over here in particular, and same thing in here. So looks like a lot of stars are going to come out of that formation. So often that external event is some kind of a shock, and the shock wave is induced, and that wave moves towards the interstellar gas cloud. And so it could be wind in this case, that the shock wave is wind. Could be any number of things, but in short, that shock wave gets induced, and that wave moves toward the interstellar gas cloud. It passes through the cloud, and it begins to compress that gas. The motion of the particles in the cloud continue moving after the shock wave passes. And the densest part of that cloud becomes gravitationally unstable. And so stars are born within that contracting region of the gas. So gravitationally unstable, gravity wants to pull you inward. So gravity is pulling inward towards the core, and gravity's pulling inward there. So it kind of becomes a little unstable, and you end up with a lot of pressure pushing outward. And stars are born within the contracting regions of the gas. So here's where they're contracting, right over here. So they're contracting here, and gravity's winning at this point. Gravity's pulling everything inward. So contracting regions give birth. So when everything's pulling in, gravity's pulling in. So gravity's pulling inward. We're going to cross these off. Gravity's pulling inward, and that makes the temperature rises. And as that temperature rises, pressure then begins pushing outward. And the temperature gets so hot that the pressure overcomes gravity, and we have that outward push, and we still have a core with gravity pulling inward, but the pressure is greater than gravity, and then we see something that looks a little more normal, like a star or a planet. So some of the sources of shock waves, massive stars that have so much mass in it often die young. Their supernova tend to happen near the site of a recent star formation. Ionization fronts of hot, massive O or B stars produce an ultraviolet radiation that could cause a shock. So this massive star dying young, a supernova, can send a shock wave when it dies. Collisions of giant molecular clouds. So these molecular clouds again are moving. So nothing's basically a steady state in astronomy or in the atmosphere, and that's pretty obvious. So here we have these giant clouds moving, and they collide into each other, and that sends a big shock wave rippling through the universe, and that shock wave can then run into another gaseous mass and cause it to contract. The spiral arms in the galaxies, like our Milky Way, we're not certain, astronomers aren't certain, but they're probably rotating shockwave patterns that caused our whole Milky Way to form and all the stars and planets within the Milky Way to form. So here's some pictures of what that might look like, of what the different sources may look like. And we see an arc of gas compressed by a shock wave forms a little supernova right over here. This is the supernova right here that's being formed. And then here's the source of an ancient supernova explosion. We know it's ancient because of how long the light takes to reach us. And then star formation right here, this compression. We're seeing a whole lot of compression here. So we're going to see quite a lot of stars form out of that. And then here's more than 40 young O and B stars that are inflating a bubble of hot gas inside the nebula from which they formed. So we have all these stars that form, and then they're inflating this bubble around it right there. So the end of a star's life now we're getting into the end of the life. When all the nuclear fuel in a star is used up, gravity wins over the pressure, and the star dies. So that nuclear fuel, that's that thermonuclear reaction. So we have helium, and we saw this in the last chapter. We have helium, and we have hydrogen, and we have a thermonuclear reaction, and that creates high temperatures. So those high temperatures create high pressure. So now when helium or hydrogen, we said that when hydrogen is depleted, the star dies, and that's the first to go. So we see all these hydrogen reactions creating this helium. So when there's no more hydrogen left, it can't create any more helium. So the star ends up dying. So when the nuclear fuel, that's this right here, hydrogen and helium, they are the nuclear fuel, and when it's used up, gravity wins. So now we no longer have this outward pressure. That's the pressure. So when the outward pressure is gone, gravity's pull inward wins, and instead of it contracting, it implodes. It basically, so we're calling it an explosion here, but gravity wins, and we see these high mass stars die first in a gigantic explosion of supernova. So when everything starts pulling inward, it basically implodes, and it gives off a whole lot of material. And if you look at page 262 of your textbook, that real pretty little image in the middle, or that the whole image really, there's the black background with the stars, but that colorful image in the center, that's the result of the death of a star. That's all the matter given off when a star dies. So these really massive stars are the ones that die first, and they die in this gigantic explosion called a supernova. Less massive stars will die in a less dramatic event, and it's just called a particular nova. So a nova and a supernova are the events that happen when a star dies. So here's a nice little picture to take a look at. That looks like a prismatic if you've ever been to Yellowstone, the thermal areas to create these prismatics. So there's a whole lot of heat. So I'm sorry, the app just crashed here. So we were saying here that all these lines right here are these spectral lines, and all these different spectral lines there indicate as they move away, the Doppler shift shows that something collapsed right there in the center, and the debris is moving farther and farther away. And then, of course, as they move away, a wind can come along, or they can collide with something else, and then form new stars. So this matter, all this material that we're looking at, all this material of the nebula, so, I'm sorry, it doesn't go away. So we were saying here that all these lines right here, when something it's not absorbed anywhere. Is what I'm trying to say. So when the star dies, different spectral the star lines doesn't disappear. It just changes as they move away. The Doppler shift shows that's in the nebula. Something collapsed right there in the center, and in the nebula is moving farther and farther away. Create new stars again. And so, then, of course, as they move away, a star that dies can give birth to many or they can collide with something else, and then form new stars. So this matter, all this material that we're looking at, and all this material of the nebula with about zero, it doesn't go away. Greater than so approximately oftentimes 0.4 of the mass times the mass of the sun. It's not absorbed anywhere. And they're completely convective. So when we see that heat, the star doesn't disappear. When we saw the sun, it just changes again into all we had this debris convection that's in the nebula right there. Well, a red dwarf is completely convective. There's no radiation coming out of it. The medium mass stars are just a little bit bigger, and they develop a helium core. And so these low mass stars are red dwarfs, and they're stars with about zero greater than approximately 0.4 of the mass times the mass of the sun, loss and they're completely convective. So when we see that heat to the sun, or when we saw the sun radiating, not close physically, we had this little convection circle right there. Well, a red dwarf is completely convective. There's no radiation coming out of it. So the medium mass stars are just a little bit bigger, and they develop a helium core, a stellar windstorm, and so here's light from flare-up of the unstable red supergiant that's shown here illuminates the gas and then the dust. It illuminates gas and dust that were previously lost. And then over here in this second picture, we see the nebula is composed of mass loss from a blue giant star and a violent stellar windstorm. So similar, very similar, not close physically, that blue star, but very similar explosion to the sun. And stars like our own sun are constantly losing mass. So the sun is constantly losing mass, and they do so. They lose that mass. Here we see a slow stellar wind from a red giant, and so the gases light of the slow wind are not really all the unstable red supergiant that's shown here illuminates the gas, and faster wind. The dust, you can tell that's faster. It illuminates gas and dust that were previously lost. Red and white, and then over here in this second picture, we see the nebula is composed of mass lost from a blue giant star. So the process that produces planetary nebulae involves two different stellar winds. A slow wind from a red giant blows away the cool outer layers of the star, and then the fast wind from the hot inner layer of the star are the planetary nebulae, and excites it. So here we see the slow stellar wind from a red giant. The cat eye, and the gases of the slow wind are not really all easily detected. We see them in the infrared right here. And then here's a faster wind. We can tell that's faster. This is a different color. Red and white typically glow hotter. Planetary nebulae and that indicates the molecules are moving faster. It's not a perfect. You can see that asymmetric pattern right here. So the process that produces planetary nebulae involves two different stellar winds, like a perfect slow shape. Wind from a red giant blows away the cool outer layers of the star. symmetric.
Well,
My
my
drawing's
not
not
inner
symmetric,
layer
but
of
if
a
you
star
had, if you took a
overtakes the
basketball
slow wind
and you cut the basketball in
excites
half,
it, so you start
you
seeing
would
this
see
little
two
cat eye
symmetric
nebula.
sides. And
The cat
but here,
eye,
we don't see that
right
symmetric
there, this
pattern.
little cat eye
We see a
nebula
lot
forming.
of irregularities
And then you see
there.
winds
So
carrying away.
the
carrying
planetary
away the outer
nebulae
layer.
are asymmetric,
And
probably
the
due
planetary
to
nebulae are
rotating.
often
The stars
asymmetric.
rotating and
It's
moving.
not a
Magnetic
you
field
can see that
swirling
asymmetric
around the
pattern
room
right
disrupt
here.
its physical shape.
Symmetric would be perfectly
and then
round.
dust around the
Or
disk,
perfectly square,
or dust
or
disks
perfect
around the
shape.
stars.
So if you
could
think
also
of
interfere,
if you think of a circle
with
right
their
there and you cut it
maintaining a
down,
symmetric pattern,
Well, my
or
drawing's not
symmetric
symmetric,
shape,
but if
really.
you had if you took a
The
basketball
helium-burning shell
and you cut the basketball
of
in
a
half,
star, as
you
it
would
dies,
see two
it
symmetric
dumps carbon
sides
and
but
oxygen
here this
onto
we
the
don't see
core,
that
and that's going to cause the core to collapse from the weight,
irregularities
and
there.
for matter to actually become degenerate.
And that
planetary
happens
nebulae
when that
are
happens.
You see
Asymmetric,
a low luminosity
probably
and
due
a high
to
temperature.
rotating.
See,
The stars
your white
rotating and
dwarf
moving,
has a
magnetic
high
field
temperature and a
swirling
low
around the
luminosity.
luminosity.
Disrupt its physical shape. And then
So
dust around the
characteristics of
disk,
white
dwarfs, so
dust
that they
disks around the
degenerate,
stars,
could also
stellar
interfere,
remnants,
with their
and those
maintaining
stellar
a
remnants
symmetric pattern,
are carbon and
or a
oxygen.
symmetric shape, really.
White dwarfs are extremely
the
dense.
helium-burning
Remember that the
shell,
more massive
of
a star is,
as
the
it
shorter
dies,
its
it
life
dumps
is.
carbon and,
So white
oxygen
dwarfs are the
onto
first
the
to
core,
die,
and that's going to cause the core to collapse,
so they don't
from the
live as
weight.
long.
And for
So
matter
here's
to
a
actually become
Hertzsprung-Russell
degenerate.
diagram
And that
of a
happens
white dwarf.
when that happens,
And,
you see
so
a
we
low
see
luminosity
here,
and a high temperature.
and we don't
See,
have that
so
real
your white
pronounced
dwarf
that mean
has
sequence,
a high temperature and
or,
a low luminosity.
here's where that mean sequence is.
But really, our
So
white
characteristics
dwarfs,
of white
dwarfs
are just
so that
a little,
they
little
degenerate
piece of that
stellar
Hertzsprung-Russell
remnants,
diagram. We don't see a really
and those stellar remnants are carbon
really
and
long
oxygen.
sequence here.
White dwarfs are
Note that
extremely
the
dense.
supergiant-
So remember that the
giants
more
and supergiants
massive
are
a
up
star
here,
is, the
up a
shorter
little
its
higher.
life is.
So they're higher in
white
luminosity.
dwarfs are the first to die.
Here's our
because
luminosity
they're so
right there. So
massive,
white dwarfs are low
so they don't live as
luminosity
long.
and high temperature.
So here's a Hertzsprung-Russell
giants
diagram
and supergiants
of a white dwarf.
are high temperature and high luminosity.
So we see here.
So these have high temperatures.
And we don't have that real
and high
pronounced
luminosity,
mean sequence.
But a white dwarf.
Here's where that
is
mean
low
sequence
luminosity,
But
and
really,
high
our
temperature.
white dwarfs are just a little piece of that Hertzsprung-Russell diagram. We don't see a really long sequence here. Note that the giants and supergiants are up here, up a little higher, so they're higher in luminosity. Here's our luminosity right there. So white dwarfs are low luminosity and high temperature. Giants and supergiants are high temperature and high luminosity. So these have high temperatures and high luminosity, but a white dwarf is low luminosity and high temperature. So towards scientists want to find causes for natural events. So they search for ultimate causes that often lead to a smaller leads to a better understanding of all the subcomponents too. So looking at why ice floats, it does so because it's less dense. But why is it less dense? So all those different questions, the ultimate causes are what scientists are always looking for. And that's no different than in astronomy. And then when we look at a binary star, we looked at stars in general, and now we want to look at a binary system. So a binary system means that we have two stars paired together, and each star controls a finite region of space, and then it's bounded by this Roche surface here. So, and that Roche surface is this one right out here, this little, and then same with the green one too. And we see here that at this Lagrange point is where they're basically, the surfaces come together and they bind. Here's L2 and L3, their lobe regions. It's the two stars right there that get bound together. So for a binary pair where the mass of B is equal to 5 times the mass of A, and for our
baseline comparisons, we'll have A being the sun. That'll be the second star here. So star B is the heavy one right here, and star B is going to be 5 times the mass of the sun. And it's going to evolve much more quickly than star A is. So B expands to a giant it expands to a giant star, and that giant star fills that Roche surface and transfers its mass now to star A. So when it transfers that mass, star B becomes a lower mass giant and A becomes a main sequence star. It's still a dwarf. Remember, main sequence stars are dwarfs. And eventually star A ends up losing its dwarf status and becomes a giant. And then it too fills that Roche surface. So we start out here, and we see the difference in pattern. It winds up being our end result. We end up seeing that flop. So the two stars in a binary star system, they're exchanging mass between them. So a binary system consists of a white dwarf and then a main sequence red giant star. The white dwarf accretes matter from the companion, or takes on that matter from its companion star. And then a nova explosion is a hydrogen gets accreted through the accretion disk and accumulates on the surface of the white dwarf. In many cases, that mass transfer, the transfer of the mass, that cycle, so you wind up, so let's look at that cycle first, though, actually. So we saw the little dwarf, and we saw it connected to this really big one, and then we saw it reverse. We saw this one with the, we saw these bubbles reverse there, or there's Roche encasings reverse. And then it continues, it oscillates like that. Then we go back to this pair, and then we go to this pair. So that cycle resumes, this cycle of mass exchange resumes after a nova explosion. And the cycle of repeating explosions happens every few years. Actually, it's a few thousand years that happens in. So high mass stars, nuclear fusion in a high mass star is really prolific. It's greater than 8 times the mass of the sun, and it gives off a pattern much like a medium mass star does until the star runs out of helium in the center. And we see that nice little red picture that it creates. So the high mass stars, again, we see that they have a hydrogen fusion cell around the outer part, helium in the center, and then a C fusion, and so on down to an iron at the core. So nuclear fusion, if a star mass is greater than 4 times the mass of the sun, when the core contracts, then you get a C fusion. A C fusion reaction begins in the core. That ignites the shell, and then we get this whole pattern going through. That's not that important. So the final stages of that fusion in a massive star leads to the formation of the iron core. And eventually the iron core collapses, and it triggers that supernova explosion that destroys the star for good. But then that destroyed star can still give birth to new stars in its supernova. So sometimes a star which exploded as a supernova can be identified on images taken before that explosion, and that's what you see right here. So supernova can be easily seen in distant galaxies. So when you look, when astronomers here are looking at distant galaxies, they can see the supernova pattern. It's a lot of that gas out there, and hundreds to thousands of years later, the ejected material from a supernova is still visible as remnants, visible to people on Earth. So a misconception is that explosions in space are accompanied by deep, loud booms, but the truth is that space is nearly a vacuum, so there's no medium through which sound can travel. So consequently, there is no sound. The only reason we hear each other is because our vocal cords in our throat are vibrating, and as they vibrate, they're pushing the air outside of our mouth. They're pushing the air, and they're making that air oscillate, and as that air oscillates, it propagates through space. It creates a disturbance. And space, I mean our atmosphere around us, not outer space. So wherever you're standing, when you begin to talk, the vibrations in your voice are pushing out or expelling air or expelling carbon dioxide into air, and they're disturbing that air pattern, and air is going to propagate that sound. It's the medium through which sound travels. But because there's no vacuum, or because there is no atmosphere or no air, basically in outer space it's a vacuum, there is no medium for sound to travel in. So in outer space there is no sound at all. So you don't hear any sonic boom or nothing in outer space. So the remnants, when a supernova, when a star explodes into a supernova, you get a real pretty colorful picture there, and they're the spectral lines. So a type 1 remnant has no hydrogen lines in the spectrum, but type 2 still has some hydrogen lines. So a type 2 means that hydrogen wasn't completely depleted. So the star died even though it still had some hydrogen left. And what would make that happen is that the temperature that pressure gravity balance, it didn't it was the imbalance was so great, or actually the relationship between the two of them tipped the balance in favor, and there was so much mass that it didn't need the amount of mass far exceeded the amount of hydrogen, and the star died. So if you had a less massive structure, chances are all the hydrogen would get used up before and then the death would occur. But something that's really massive, that's going to die into a supernova, the mass itself far exceeded hydrogen, and that's why you would still have some hydrogen lines visible. And we'll see, what you're looking at here is the Crab Nebula. So supernova remnants, again, we have the Cygnus Loop and Cassiopeia. So they're pretty popular images in the night sky. So in this case, shocks of supernova remnants accelerate protons and electrons to really high energies. And those really high energies means that they're traveling really fast. So that's a cosmic ray, or what's termed as a cosmic ray. And then when those rays are traveling in a magnetic field, those electrons are going to rotate. They're going to be bounced all around. And we see that spiral nature shown in the picture here. So here's a famous supernova of 1987. And that star, the star that exploded, we see that supernova in 1987. It was fortunately captured by a very high-speed telescope, or telescope with a camera on it. And the remnants of that supernova, we see that ring pattern. So that's how astronomers are able to conclude that the Milky Way's ring patterns are probably supernovae or died, or stars that died. So nearby supernovae, nearby means less than 50 light years away. That nearby supernovae can kill many life forms on Earth through gamma radiation and high energy particles. But at this time, no star is capable of producing a supernova that is less than 50 light years away. So the most massive star known is about 100 times the mass of the sun, and it's about 25,000 light years from Earth. So we don't have to worry about being extinguished by a supernova. So the Earth will come to an end at some point. The sun's going to expand into a red giant in about 5 billion years, and it expands. And when that happens, it's going to expand to approximately the Earth's radius. And when it does, it's going to incinerate the Earth. It's going to be so hot. The sun and Earth, the amount of thermal energy given off by the sun when it equals the Earth's radius, or expands to the Earth's radius, the sun is going to be so hot at that point that nothing on Earth is going to survive. So Earth will be incinerated. So the sun may form a planetary nebula, but we don't know that. Astronomers don't know it yet. It's just a hypothesis that hasn't been proven. And the sun's carbon and oxygen core is going to end up becoming a white dwarf. So that's another form of a star again, remember? So it's a white dwarf now, and then it's going to grow into a red giant, and eventually go back to being a white dwarf when it gives off a lot of that heat again. So one thing I want to point out, we talked about this part right here about the relative nature, the sun expanding the Earth's radius. So a lot of times we think the sun is bigger than the Earth. Well, that's not true. That's another misconception. So the Earth is rotating around the sun. So the sun is a star, and the Earth is rotating it around it, and then so are the other planets. All the planets are rotating around that sun there. But the sun is not bigger than the Earth. When it gets to that point, when it gets to be the same size as the Earth, it's going to incinerate the Earth. So Ring Nebula, another little picture there of those spectral lines. So don't worry, you don't have to answer these discussion questions. The homework is there for you. But basically, why can't low mass main sequence stars become giants? There's not enough fusion going on. There's not enough molecules. The hydrogen and helium elements aren't prolific enough to make it grow into a giant. And then is fusion of the lightest elements in the core of a very massive star in the center, in the innermost shell, in an inner shell, or in an outer, or the outermost. The later ones are on the outermost, and the heaviest are on the interior. And Earth's day and night would look like when the sun becomes a true white dwarf. It wouldn't be as bright. We wouldn't have as much to see. We would still see phases of the moon, but again, the sun pretty much still is a white dwarf right now, and it's growing, and then eventually it'll go back to being that. So if that's pretty much everything for our lecture here, and if you have any questions, please do reach out.